Okay, today we're going to do the second video on volume, and I think this is definitely the hardest one. So we'll do a bunch of practice in class with this. So we learned last class the disk method. We use when the cross sections are shaped like disk, and we have the radius of a cross section is determined by a single function f of x. The area of the disk is pi r squared, and then to get the volume we take the area of a circle and multiply by the width, which is dx or dy, and that's what we did in the last video. In this video, we're going to do the washer method, which means we're going to rotate two curves and there's going to be a hole in the middle. So the washer method is used when the cross sections are washer shaped. The radius of a cross section is determined by two functions. This gives us two separate radii, an outer radius and an inner radius. And the area of the washer formula is pi, the outer radius squared minus the inner radius, and it shows. So when we do these, what we're technically doing is we're taking pi and then the area of the whole circle, which would be pi outer radius squared, and then dx or dy depending on where we're going, and then we would subtract the area of the inner circle, which would be pi inner radius squared, and then dx. These should be the same variables. So we're taking the area of the entire circle, which is made by the outer curve, and subtracting the area of this little circle so that we can get what's left over, which is the washer. We have to do this because we don't know the formula for a washer. Now they usually combine this, is where they pull it into one integral because the bounds will be the same. And since there's a pi in both, we can just pull it outside of both, and then they just say outer radius squared minus inner radius squared dx. So we're going to do these. My graphs are not the best, so if you can draw better pictures, please do. But if you click on the link here, it kind of shows you better pictures of washer method and goes through the steps so that you can actually see the 3D pictures that I'm not very good at drawing. So we use washer method when we want to find the volume of a solid formed by two curves, when they're rotated around an axis or around a line like x equals 1 or y equals 1. So the steps are pretty much the same. We graph the two curves. We would determine rectangles. This should say rectangles. Rectangles perpendicular to the axis of rotation, and determine the variable of integration. We have to find the outer radius and the inner radius, and then we plug into the formula. So if I let f of x be my outer and g of x be my inner, the formula is pi, the integral of whatever my bounds are, of f of x squared minus g of x squared dx. And then this also can be in terms of y, so it could be f of y squared minus g of y squared dy. Then we find the limits of integration, and then we integrate to find the volume. So it's the same steps, but it's just a little bit more difficult because we have two curves. And the key thing is to identify what's the outside curve and what's the inside curve. So for our first example on this, let R be the region bounded by the graphs y equals 2x squared, y1. So my bottom one is y1, and y2 is x plus 1 in quadrant 1 only. Find the volume of the solid generated by rotating around the x-axis. Assume x and y in feet. So I tried to draw, it's not the best, but I tried to draw a 3D picture of this. And so you'd have a hole in the middle. The outside of the washer would be determined by y2, and the inside would be y1. And so I'm going to draw two rectangles, one for my outside rectangle, one for my inside radius. So y2 is my outside radius, that's here, and y1 is my inside because we want to get rid of that hole in the middle. So both of them are perpendicular to dx, to the x-axis, so it's dx. My variables of integration are on the x-axis, so it's 0, and then when they intersect, so you can either algebraically set them equal to each other. Generally, if you have a calculator, you can figure out where they intersect, but I'm going to set them equal to 0. I'm going to factor these two equations. So you can factor by grouping. I'm just going to do guess and check. So 2x squared, it has to be 2x and x. It has to multiply to -1, but I need to make sure the middle adds up to -x, which means this 2 has to be a negative. So I'm going to have -1 plus 1, because then if I would multiply this out again, I would get a -2x plus a positive x, which would give me a -x. And then I set each one equal to 0. So x is -1/2, or x is 1. We want the first quadrant, so it's going to be x is 1. So we're going to go from 0 to 1. And then we're going to do outer radius minus inner radius. I'm going to put my pi outside. So the outer radius is this y2. So it would be technically y2 squared minus y1 squared. It all has to be in terms of x. So y2 is equal to x plus 1. And then y1 is equal to 2x squared. And then just make sure you square it again. And just be careful, guys, that the biggest mistake people do is they do outer minus inner and then square it. You have to square each one first and then subtract it. So just be very careful with that. And then if you plug that into your calculator, you would get 23/15 pi. And you can pause and check and make sure that you get that when you do it on your calculator. Okay, so for the next example, we're going to find the volume of the solid obtained by rotating the region the square root of x and y equals x about the x-axis. So I already drew it. This is my square root of x. This is my y equals x. I'm going to call the square root of x y1 and y equals x y2 just to help us when we're doing this. And so I'm going to set up my formula again. I have pi, the integral. Okay, so I'm drawing my two rectangles from the outer curve and from the inner curve to what I'm rotating around, because that gives me my radius. So my outer radius is going to be y1. So I'm going to have y1 squared minus my inner radius, which is y2. And then what we should have done already is figured out that it's perpendicular to the x-axis, so we're in terms of dx. And then our bounds. So our bounds are from 0 and where they intersect, and if you graph them, you can easily tell that it's intersecting at 1. If you set them equal to each other algebraically, you probably just have to think about it, and so say, well, the square root of x is equal to x at 0 and 1. It's not really easy to figure it out algebraically, but you could square it both sides and then get everything to one side and then factor. So you'd get 0 is equal to x times x minus 1. So that's how you would solve it algebraically. But you can just guess and check or graph it, and it's easy to see. And then because we're in terms of dx, we need everything in terms of x. So I'm going to have 0 to 1. y1 is the square root of x squared minus y2, which is x squared dx. And then again, you can pause the video to put this in your calculator. I did it ahead of time to save time, and so when I put this in my calculator, I got 1/6, and then I would have pi. So that would be my volume, and then I would have units cubed again. So go back and put the units on the last one. We forgot to do that. Okay, the next example is we're rotating around the y-axis. So we're going to find the volume of the solid obtained by rotating the region, the same curves again, square root of x and x, about the y-axis. So what changes is we're going to be all in terms of y, because we're going perpendicular to the y-axis. So pi, integral, and we have to remember it's dy. That's the key thing. So when we do our outer radius is this curve. So this distance is x. It's going to be determined by our curve. So that curve, let's call this y1, y2, which would make this our x1 and x2. So this is going to be my y equals x, my second curve. And we need to solve for x, which it already is in this case. So that's my outer curve. So my outer radius is x or y, which is equal. So we're going to have y squared minus my inner radius is this x distance. So I have to solve for y, so I square both sides. So x1 is equal to y squared. So I'm going to have y squared, and then I have to square it again for my radius, and then my bounds are on the y-axis. So this point is 0, 0. This point we figured out was 1, 1 in the example before. So again, I'm going from 0 to 1. And then when you plug this in your calculator, you're going to have to use the X button in your calculator because there is no Y value, but you should get the same answer. So you can pause the video and then check if you get the same answer as I do. And you should have got 215 over pi if you did it correctly. 215 times pi. And then again, they don't give me units, so I'm going to say units cubed, and this is my volume. And just if you switch your curves, you'll end up getting a negative number. You'll probably get the same volume, but a negative number. So that means you have to go back to the first step and switch them and then make your value positive. Okay, so the last two examples, or last three examples, are going to be rotating around a line other than the x and y axis. So this example says let R be the region bounded by y equals 2 the square root of x minus 1 and y equals x minus 1. Find the volume of the solid resulting from rotating the region around x equals negative 1. So these curves are kind of it. I couldn't find a picture of exact the curves and I was having trouble drawing them. So we're just going to pretend that this curve is y equals x minus 1 and this curve is y equals 2 the square root of x minus 1, just to get an idea of what it looks like. And so this is actually the curve. It goes from 1, 0 to 5, 4 it should be if you graph it. Okay. And you can graph that on your calculator or make a t-table to do it by hand. But it would look like this, so you'd get a 3D figure. That kind of looks, I would say, like a flower if it's rotated all around. But the outer radius is determined by the pink line curve, which is the linear curve, y equals x minus 1, and the inner radius is y equals 2 the square root of x minus 1. The difference, though, is that the radius is no longer just the curve, because what we did is we moved it over. We shifted it left 1. So when we do this, okay, we're going to have this distance, like for my inner radius, which is x, but then I have to subtract the radius. So when we do this, we are going to take our curve and we're going to subtract our radius from it, our line that we're rotating around, and that will give me the radius. So we're going to take our curve and we're going to subtract the line that we're rotating around, and that will give me my outer and inner radius. So that's this distance is my inner radius. All the way to here is my outer radius. And so the radii have both been increased by 1. We can see it's been moved left 1, so it's been increased by 1. So when I integrate, again, we're going perpendicular. We draw our rectangles. We're perpendicular to x equals negative 1, so the change in this is on the y-axis, so it's dy. So everything's going to be in terms of y. So that means we have to solve both of these equations for x. So this becomes x plus 1, or y plus 1 equals x. This one I'm going to divide by 2. That gives me the square root of x minus 1. I have to square both sides, so I get y squared over 4 is x minus 1. So then when I solve it, I get x is y squared over 4 plus 1. Okay, so those are my two equations for x. Just to make this, we'll say this is x1 and this is x2. And so we're going to put our pi. Let's find our bounds because it's a little bit easier. They have to be on the y-axis, so the lowest it is 0, and then we found that they intersect at 4. So when we have two curves, it's always where the two curves intersect if they don't give us bounds. And so when we do this, we're going to take our outer radius, which is y plus 1, and we're going to subtract our line, which is negative 1, and that's going to give me my new radius. So we're doing minus a negative 1, which is plus 1, which we can see because it was increased by 1. And then we're going to do minus, and then we have to do the same thing for our inner radius. So our inner radius is this curve, which we said is y squared over 4 plus 1. So we're going to take that curve, and then again we're going to subtract our line, which is minus negative 1. And the reason we don't have to do this when it's the x-axis or the y-axis is because those are the lines x equals 0 and y equals 0, so we're just subtracting 0, so it doesn't matter. And so it always helps to kind of condense these a little bit. So we get y plus 2 squared minus y squared over 4 plus 2 as well, squared, I forgot the squared up here, dy. It kind of helps to condense them before you put it in your calculator. If you didn't have your calculator, you'd have to square all this out, like using FOIL or distributing it, and then integrating each term separately. But if we do this on our calculator, just pause the video and try it on your calculator, and then we can check our answers. Okay, so you should have got 96 over 5, and then we have to multiply by pi, and we're going to put units cubed again. Okay, and then I'm going to let you try this example. I kind of drew it, but I want you to actually try this example on your own to make sure that you know how to do this. And then I'll come back and give you the answer after we do the last example. So I want you to try this one. We're going to do example 7 together, and then I'll give you the answer to example 6 for you to check it. So example 7 says determine the volume of the solid obtained by rotating the region y equals x squared minus 2x, so that's this, and y equals x. So you will probably want to pause the video, graph them on your calculator, and sketch them. And we're going to rotate it around y equals 4. So it's going to make this curve up here, which I'm not going to draw. But if you haven't drawn it already, just pause the video and draw it. After you have drawn it, we're going to figure out what our outer radius and our inner radius is. So we're going to draw two lines, the distance of our outer radius and the distance of our inner. So again, we draw our rectangles first. We figure out our variable of integration, so it would be along the x-axis, or a line, or the width is dx. So we're going to integrate for dx. So let's do our bounds. Our bounds have to be on the x-axis. So they're going to start at 0, which is where it starts, and then where the two curves intersect. And so the easiest way is to graph these two curves and figure out where they intersect, or you can also set them equal to each other. But just to save time, we'll just do it graphically. So I graph them, and they intersect at 3, 3. So the x value is 3. And then we have to figure out our outer radius and our inner radius. So in this case, it won't technically matter because we're squaring it, but we always want to do the more positive minus the less positive. So when we subtract our radius, our radii, to figure out our radius, when we do 4, we're going to actually do 4 minus our curve, because this distance is going to be this minus whatever our curve is, and that's going to give us our radius, what is left over. So to get our outer radius, we're going to do 4 minus the outer curve, which the nice thing, it's already in terms of x, which is x squared minus 2x. And that needs to be in parentheses because you'll have to distribute the negative. And then my inner radius is this distance, which we're going to take 4 and we're going to subtract this curve, which is just x. Now, it won't technically matter if you did x squared minus 2x minus 4 because you're squaring it, so it technically won't matter. But the correct way is to do the more positive minus the negative. So 4 is more positive than any of these y values on either of these curves, which is why we did 4 minus that curve. And then you're going to put this in your calculator. So after you put this in your calculator, you should get 153 over 5 pi. Make sure that this x squared minus 2x is in parentheses, and then the squared is around both the 4 minus that whole quantity. Okay, and then also the 4 minus x, and we should get 153 over 5. And then if we come back to this one, and if after you try it, you should get the volume to be 8 pi units cubed. So try that setup, and we will definitely practice more with this in class. This is definitely very challenging, which is why we're doing the flipped class for this unit. Okay? So that's it for the lesson on volumes, and I'll see you tomorrow in class.